Hello, I'm going to be showing you guys some sorting and searching algorithms today. Starting off with right here on this graph is going to be a few different points on this graph with weights in between these points. So this represents a few cities here around here. We got Phoenix, Santa Fe, Houston, Dallas, Oklahoma City, Kansas City, and Memphis. So we want to find what is the shortest path between some of these cities. As you can see, there are multiple routes that can be taken to all of these places. Um, so yeah, let's get right into it. A lot of this stuff is useful. Yeah, I have these maps here just because it's very similar to Google Maps, or just trying to figure out how to get somewhere pretty fast in a car. You'll just plug in those directions to Google or Apple Maps, and it'll give you the shortest route. So that's when these algorithms are useful, and I'll demonstrate a few. So first off, we'll start with Dijkstra's algorithm, and we'll go from Memphis to Phoenix here. So to us, it might seem like the most obvious path is through here, through Oklahoma City, and then Santa Fe over to Phoenix. But let's find out. So if we start at Memphis, then go to Phoenix. Um, Oops, I forgot to clear that graph there. All right, and there we go. So same graph, but now we get down here. It says Dijkstra's shortest path from Memphis to Phoenix is from Memphis, Kansas City, Santa Fe to Phoenix. So it does avoid this Oklahoma City that I originally thought, and goes right to Phoenix, right down here. But what happens if we add a new kind of node or hub right here with some weights? I'm gonna take this stuff from the Power Grid board game, and I'm gonna do the Denver to Santa Fe and then the Denver to Phoenix. So Denver to Santa Fe is going to be have a weight of 13. I will submit that edge here. And I want to make sure that I am choosing this multi-way connection. That way I can go both back and forth between the two. So we added Denver and Santa Fe. Now, let me find Denver or Santa Fe to. Oh, no, sorry. We already have Santa Fe to Phoenix. So now, when we show the graph, let's do Memphis to Phoenix again. And um, yeah, so it gives us the same um, way right there. We can see right here, the shortest path goes from Memphis, KC, Santa Fe to Phoenix, which would make sense because, as you can see, Denver and Phoenix are not connected since the shortest path is between the two there. Um, but I believe we can add one from Kansas City to Denver. So Denver to Kansas City is going to be 16, as we can see right there. So we'll add that real quick into this algorithm. Start node Denver, KC with 16. And now I'll submit that edge to the graph. I'm just going to plug in Memphis to Phoenix one more time. And we can graph. So now we can see they're a little bit more connected, but it is still giving us that shortest path right there with a weight of 46. So now I want to go ahead and try some different areas to go to that might not be as obvious with some different algorithms. So let's go from, say, start with Memphis and end in um, Denver, since we got Santa Fe and Kansas City. Memphis to Denver. Looks out of that, and this time we'll choose Bellman-Ford's. Main difference between Bellman-Ford and Dijkstra's algorithm is that Bellman-Ford can deal with negative weights, but to demonstrate its functionality, it should only graph if there are no negative weights. So now we can graph, and there we go. It also gives us the shortest path which is from Memphis to Kansas City to Denver with a weight of 28. So we can go ahead and do one more demonstration here. Let's go from Dallas to Denver. Since there are about 4 different options to get there, I feel like that'll be a good one. Dallas to Denver, and we'll use the Bellman Ford again. Oops, forgot to X out of that. All right, now we can see the graph here. And from shortest path from Dallas to Denver, it's going to go Dallas, Oklahoma City, Kansas City, and then Denver. So I want to try it one more time with Dijkstra's algorithm just to see if it gives us the same answer, which it should. And there we go. Dallas, Oklahoma City, Kansas City to Denver with the same 27. And then real quick before I let you guys go, we'll show you all the edges here. So here is a look at all the edges or nodes, you could say, or nodes with the edges. So feel free to pause, take a quick look here. You can look at them all down there. That's going to be all. I hope you enjoyed looking at these sorting algorithms as much as I did, and I hope you have a good rest of your day.